Welcome to the Math Fun Room. You know the place. You love it. It's a lot of fun. It is always a party in the Math Fun Room. Alright, in this video, I want to take a look at applications of implicit derivatives. So in a prior video, we discussed the skill of implicit differentiation. And in this section, this video, we're going to discuss word problems, if you will, applications that involve implicit derivatives. Alright, so I paused the video just to write down the first application I want to look at. Writing these out gets a little lengthy. I didn't want to have to force you through watching me write this. Right, so go ahead and pause the video yourself, and that way you can write the problem down. And when you're done writing that down, unpause, and we will pick up where you left off. Alright, now that you have unpaused the video, we're going to take a look at this first application. We're going to take a look at probably 5 or 6 word problems, different applications of implicit derivatives. And here's our first one. So this one says, suppose that oil spills from a tanker and spreads in a circular pattern. If the radius of the oil spill increases at a rate of 2 meters per second, how fast is the area increasing after 10 seconds? Right, so geometrically speaking, right, we're talking about a circular pattern, right, and we have a radius of a circle. And we're being asked to find how fast the area is increasing. Right? So we're wanting to know the rate of change of area. So we know the area of a circle is pi r squared. Right? And what we're being asked to find, right, is how fast is area changing over time. Alright, so if we talk about, or the problem gives us information, right, but if we talk about how the radius is increasing as a function of time, right, we think of, right, r of t as being an equation. Right? This is the radius as a function of time. Now let's pretend we don't know what that is yet. We just know there's some equation that describes how radius changes over time. Now if we think visually again, right, obviously as radius grows, the circle's going to grow. Right? So technically area is also a function of time. Right? Area, right, is also a function of time. I'm going to get lazy and say function and abbreviate that. So if we think of a equals pi r squared, what we really have in this case is a equaling pi r squared being, area as a function of time. And then we have rate as a function of time as well. Sorry, radius as a function of time as well. So what we're being asked, right, is how fast is the area increasing? So there's our derivative of area, like we talked about over here. Right? So our implicit differentiation, like we talked about in that prior video, says what we're going to do is differentiate with respect to time both sides of my equation. So I'm going to differentiate with respect to time the left-hand side, and I'm going to differentiate with respect to time the right-hand side. So this involves an implicit derivative. Right? So what I'm going to do in this case, I don't really know what this equation is. So I know its derivative is a prime, right? dA dt. And I don't really know what r of t is here, but I know its derivative would be r prime, dr dt. Now I'm going to pull the constant out. Then if I differentiate r squared, I get 2 times r to the first, and then times the derivative of the inside. So the derivative of the inside is r prime, right? It's dr dt. Okay. So here's our implicit derivative, where we're differentiating really the r variable with respect to time, and we're differentiating the a variable with respect to time, knowing conceptually that area really is a function of time and radius really is a function of time in the context of this problem. Excuse me. So what we're being asked to find is dA dt. This is what we're looking for, and we have an equation that tells me what dA dt is. So in order to find a numerical value for dA dt, I need to know numerical values for radius and its rate of change. Right? And I should be given that within the verbiage, right, of this problem, within my application. Now I was told, if we scroll back up here real quick, I was told that the derivative of radius, right, the rate of change of radius is growing. Okay, so let me pick red here. Right, so the radius of the oil, right, so this increases at a rate of 2 meters per second. The radius is increasing at a rate of 2 meters per second. So I have dr dt. If I scribble over here, right, I have dr dt being 2 meters per second. Right, there's my rate of increase. Now, if we scroll back down for a second and we look at my derivative formula, I also need to know the radius. So I need to know what the radius is. Well, I'm being asked to find this rate of change of area at 10 seconds. So if we think about this, right, what's the radius at 10 seconds? What's the radius at 10 seconds? Okay, so we know that we were told the radius was increasing 2 meters every second. That's its rate of change. So if I know the radius is increasing 2 meters every second, right, at the end of the first second, it has grown from 0 as a radius to 2. And then for the next second, it grows 2 more. So at the end of the first second, I have 2 meters. At the end of the second, I have an increase of 2 more meters. At the end of the third second, I have an increase of 2 more meters. At the end of the fourth second, I have an increase of 2 more meters, so on and so forth. So we can see that the time we're doubling. The time we're doubling. So technically, I'm going to double the 10 seconds. Excuse me. I'm going to double the 10 seconds, and that's going to give me the meters in my radius. Right? It's going to give me my radius in meters. So I know my radius is 20 meters. I know my rate of change is 2 meters per second. We'll be able to plug all of this in. So we're going to have pi. Let me switch colors. We have pi times, I didn't switch colors. My pen is not cooperating today. So I have pi times 2, and we know the radius now. After 10 seconds, the radius is 20 meters. And then we know that the rate of change of radius was 2 meters per second. So that's going to give me A prime. That's going to give me my change in area over time. So we can see we get 20 times 20, excuse me, 2 times 20 is 40, times 2 is 80. So I have 80 pi. And then we can see, right, meters times meters would give me meters squared per second. And that's what the change in area should be, right? Area's units are square meters, and my time unit in this case is second. So we can see there's our value. All right, so every problem we do in this section is going to be very similar to this one. In other words, we're going to write a formula for whatever it is we're trying to find. In this problem, we're trying to find the rate of change of area with respect to time. So we started by writing area that we know geometrically. And then we differentiated implicitly. So we took the derivative implicitly. Once we take that derivative implicitly, in this case, here's our unknown, dA dt, and then we have to have numerical measurements for the other quantities. And that's going to be the approach that we take on all the rest of the examples that we look at. All right, pause the video again because I wanted to write down the verbiage of the word problem. So you go ahead and pause, write this down, and when you're done, unpause, and we'll take a look at this together. All right, so now that you have written the problem down, this problem presents to us that a cylindrical tank with radius 5 meters is being filled with water at a rate of 3 cubic meters per minute. The problem asked, how fast is the height changing? So, if I think visually, have a cylindrical tank. I'm going to do my best to draw a cylindrical tank here. So here's a cylindrical tank, not the best. So I know that I have a radius of my tank, and I know that I have a height to my tank. Now I'm going to use the volume formula of a cylinder. And the reason I'm using a volume formula is I'm told that it's being filled at a rate of 3 cubic meters per minute. Okay? So it's being filled right, with a rate of 3 cubic meters per minute. So this is my change of volume over time, right? We can look at our units to see what that is. So change of volume per unit time. So I'm going to come down here, right, since we're discussing that. My change of volume per unit time is 3 cubic meters per minute. So I have to use the volume formula in order to tack this problem, if you will, right? So what is the volume of a right circular cylinder? Well, the volume of a right circular cylinder is really the area of the base, pi r squared, and then times the height, times h. So there's my volume formula. All right, now keep in mind what we're thinking of is as this volume increases, right, as the water in the tank rises, the radius and the height are functions of time. So radius changes as a function of time, height changes as a function of time, so on and so forth. So I really am taking the derivative of, with respect to time, both sides of this equation. So I'm going to differentiate v, and I'm going to differentiate pi r squared h. Right? Conceptually, that's where we're starting with. So we have r squared, pi r squared h, and v on both sides of our equation. So again, we're starting with volume because we're given the rate of change of volume. All right, now I'm going to go ahead and write symbolically what we did in the last problem, in the sense that volume is changing per unit time, and that technically, excuse me, I pulled the pi out a little too soon. Well, let me go ahead and pull it out, right? Remember, pi is a constant. So I'm going to pull the pi out, and I'm going to differentiate. And I'm thinking of, radius as a function of time, and height as a function of time. What I'm going to start doing after this problem is not write those symbols. I'm not going to write r of t, h of t, v of t. We're just going to remind ourselves that all of these variables change over time. I just don't want to have to write the function notation here. All right, so when I do this derivative, I have, the derivative of v with respect to t, which we usually get lazy and write as v prime. So I think I mentioned this in the video where we talked about implicit derivatives. What I like about the Leibniz notation is it clearly communicates to me my dependent variable is volume, my independent variable is time. And with the prime notation, I can see that v is my dependent variable, but the prime doesn't really tell me what the independent variable is. But we're going to get lazy, we're going to use the shorthand notation, and we're going to point out to ourselves that in this problem, the prime means with respect to time. So let's keep that in mind. That's what our prime means. Now I have a constant here, and I'm going to have to do a product rule here, right? So I have r of t times h of t, and I'm going to have to do a product rule. So I'm going to do derivative of the first. So when I differentiate r of t squared, I'm going to bring the power down and then multiply by the derivative of the inside. Right? So again, bring the power down, take one away. So I have 2 times r to the first power, that's what I have here, and then times the derivative of the inside is r prime. So there's derivative of the first times the second, and plus first times derivative of the second. And the derivative of h with respect to t is dh dt, and there's my h prime. All right, so what I was being asked to find here was how fast is the height changing. So I need to know r, I need to know r prime, h, and v prime. Now in the problem we scribbled, and it's above there, we were told v prime was 3 cubic meters per minute. We were told in the problem that well, we didn't know r prime, did we? All right, so let's think about this for a second. We need to figure out r prime, and h. So if we come back to this problem here, what is r and what is r prime? So we were told the radius of this tank was 5 meters. So this is my r value, right? Here is r. Right? And then we need to know dr dt. We need to know r prime. Now if we think about this geometrically for a second, if this is r, the radius is never changing. The radius is the same radius no matter how the water fills here, right? So as the water's here, as the water moves here, as the water moves here, the radius is not changing. Only the h is changing. Only the height of the fluid changes. Radius does not change. So technically, the r dt is 0. There is no change in radius. So we know my radius was 5, but my rate of change of radius is 0. So the radius is 5, but the rate of change of radius is 0. So that doesn't, what that means is it doesn't matter what h is. This is all going to be 0. All right, now again, radius we knew was 5. And h prime is what I'm looking for. I'm looking for how fast does the height change while the volume is filling the tank at 3 cubic meters per minute. So we can see that we can now solve for, this is h prime here. So now we can solve for h prime. So I'm going to just take the 25 pi divided over and have 3 over 25 pi equals h prime. I could get a decimal for that if I wanted to. I'm going to leave it in an exact form. And if you think about, what is h prime, right? What is the units for height over time? So, right, height is going to be given in terms of meters, and then time is seconds. So there is my rate of change of height per unit time. Now again, just to point out to you, what we did here is we started with volume formula for the cylinder because that's the unit that we were given. One of the units we were given radius as well, but the unit we were given here is that the tank was being filled 3 cubic meters per minute. So we had to start with the volume equation here so that we could take its derivative to be able to plug in dv dt. When we start with the derivative, we do an implicit differentiation, and we had to do a product rule here. And then once we do our product rule, we have some quantities that we need to know. We need to know r, r prime, h, and r we already knew, right? We were looking for h prime, and we also knew v prime. Plug in all that in, and we can find the value of the rate of change of height per unit time. All right, so pause the video again to write this problem down. This one's a little lengthier, so please go ahead and pause your video to write this down, and when you're done, unpause and we'll pick up together. Okay, now that you have unpaused the video, here's the scenario presented to us. We're told that a camera is set up 500 feet from a model rocket. After 3 seconds, the rocket is traveling at a speed of 20 feet per second. So letter A says how fast is the distance from the camera to the rocket changing, and letter B says how fast is the angle of elevation changing. And again, I got to scroll on my digital paper here. But first, I want to draw the scenario that we have. Right? So we have in this situation, let's say we have a camera here, and we have the rocket launch pad here. We're told that the camera is 500 feet from the rocket, and the rocket is launching. Now let's assume the rocket launches straight up. So at 3 seconds, the rocket is traveling 20 feet per second. So here's the distance from the rocket to the camera, right? Our hypotenuse. Right? And we want to know how fast is this changing. So if we think of Pythagorean's theorem here, let's say we have a and b and c, we're going to use a squared plus b squared equals c squared. And what we want out of this equation is how fast c changes with respect to time. So if b is changing 20 feet every second, how fast is c changing at that moment? So we're going to differentiate this equation with respect to time, and then we'll be able to find dc dt. So that'll be part A. So let me go ahead and scroll down here, and let's work through that differentiation. So we're going to take the derivative with respect to time of both sides of Pythagorean's theorem. Now again, I'm going to get efficient and lazy here. We're thinking of the side A changing with respect to time. We're thinking of the side B changing with respect to time. And we're thinking of the hypotenuse C with respect to time, right? It changes with respect to time. So these are all implicit derivatives. So when I differentiate A squared, I'm going to have 2A times dA dt. I'm going to be lazy and call that A prime. And when I differentiate B squared, I'm going to get 2B, and again, times dB dt. I'm going to call that B prime. And then derivative of C squared is 2C and times dC dt. I'm going to call that C prime. So C prime is what I'm looking for here. So I need to have a value for C, for B prime and B, and for A and A prime. Now, if we come back to our triangle here, we can see that if I call this A, right, let's say A is 500. C we don't know yet. And if we know that B is changing 20 feet per second, at 3 seconds, this is going to be 60. So at 3 seconds, we know that B is 60. So I'm going to plug into Pythagorean Theorem to find C. So I know 500 squared plus 60 squared equals C squared. Then whatever 500 squared plus 60 squared is, I'm going to square root that and get C. I'm not going to bother to work out that number yet. Whatever that number is, that is my C value. So what are my other quantities? So I know C, looking for C prime. I know B, we found that out, B was 60. B prime, I was told, is 20 feet per second. We know A is 500 feet. And then what is A prime? Well, similar to our cylinder problem that we just did, what's this distance? It's 500. And how does this distance change? It doesn't. So since this distance stays the same, its change is 0. There is no change in that distance. So we have A being 500 feet, but A prime is 0. We have B being 60 feet, and B prime is 20 feet per second. We have 2, and then C is whatever that number was from our hypotenuse, and then C prime, that's what we're looking for. Got a little cluttered there, I apologize. So we're looking for C prime, right? So to find C prime, we're just going to take this coefficient, if you will, and divide it over. So we have whatever 2 times 6 times 20 is. I'll figure that out in a second. 2 times 60 times 20. And we'll divide by 2 times square root of 500 squared plus 60 squared. So that's my C prime. So let's see, I could simplify a little here. The 2's cancel. 6 times 2 is 12. So I'm going to have 1200 over whatever that number is. And again, I'll take out a calculator and crunch that in a second. So that's the change of the hypotenuse over time. Right? We're going to have feet per second. So plugging all that in, I get that C prime is approximately 1.18 feet per second. Okay. All right. Now, let's look at letter B. So letter B said, how fast is the angle changing at that same moment? So letter B, how fast is the angle changing at that moment? All right, so again, let me just sketch my triangle here. What's the angle of elevation? We're looking for the change of this angle, right? We want d theta dt is what we want within that triangle. So again, we had called this A, we called this B, we called this C, and we knew what those quantities were. A was what, 500, B was what, 60, and C was the square root of 500 squared plus 60 squared. That was our values there. Right? We also knew what dB dt was, right? B prime was 20 feet per second. We knew A prime was 0. And we got C prime to be approximately 1.18 feet per second from that last problem. So here's all the information that we have. Now, if I'm going to find d theta dt, obviously I'm going to have to use some type of trig function. So I could use cosine of theta being a over c. I could use sine of theta being b over c. I'm going to use sine of theta as b over c, just because I can. Right? What is going on there? Get out of my way. All right, so I'm going to use sine of theta. And let me see, I don't want to scroll too far down. So I'm going to involve the equation sine of theta equals b over c. Now what I want is d theta dt. Right? So I'm going to differentiate with respect to time both sides of my equation. All right, so again, I'm assuming that theta changes over time, which we know that it does, right? As the rocket rises, right? This angle is going to grow and grow. And then we know B changes over time, right? The rocket is rising. And we know C changes over time. We got that guy there. So let's see, if I differentiate with respect to time here, we have derivative of sine is cosine, and then times the derivative of the inside. And I'm going to have to do a quotient rule here. So I'm going to have bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. Okay, so I need to know all of the quantities except theta prime. Theta prime is what I'm looking for. So I need to know c, b prime, b, c prime, and c squared. And I need to know the cosine of theta. Now if we scroll back up to our triangle here, what is the cosine of theta? Well, the cosine of angle theta here is adjacent over hypotenuse. So 500 divided by the square root is cosine of theta. So cosine of theta is 500 over the square root of 500 squared plus 60 squared, whatever that number is, times theta prime. Right? And then we have c. So c was the 500 squared plus 60 squared square rooted, and b was 20. And then minus, b prime was 20, b was 60, and c prime was said was about 1.18 feet per second. And again, c was my hypotenuse, and then we're squaring c. We have c squared here. All right, now I'm going to crunch this out in just a moment. What I'm looking for is theta prime. So theta prime, I'm going to basically divide by its coefficient or multiply by its reciprocal. So I'm going to multiply by the reciprocal. I'm going to have 500 squared plus 60 squared as a root over 500. And then times all of the stuff I have up here. 500 squared plus 60 squared square root times 20. And then what do we get? Minus 60 times 1.8 all over. And I'm going to have 500 squared plus 60 squared square rooted all squared. I'm going to do a little bit of cleanup here. So just a little bit of cleanup. I have this radical times itself. So I could cancel one of those out. And I have just that guy to the first power. So what I end up with then is theta prime being all of this stuff, right? So I have 20 times the radical of 500 squared plus 60 squared minus 60 times 1.18. And then all over I have this 500, and then I had one of those radicals left over. Alright, so I paused the video for a second and I plugged all of that into Desmos, and what I'm getting is 0.04 if I round to 2 decimal places. So I'm getting this to be theta prime about, let me say, approximately 0.04. Now if we keep in mind with trig functions, right, what did we say? Cosine of theta was 500 over the radical, right? And so what I have is feet over feet, which is unitless. So that was what we always called radians in a trig course, right? So trig ratios are always unitless, right? So the angles are radians in that case. Technically, radians are unitless. Right? So again, go back to a trig class to see that conversation. But in this case, our angle theta changes 0.04 radians per second. All right, now I really love that example. That's a really fun example because it involves two things for us. One, it involves Pythagorean theorem, right? Finding the change of one side, right? And then finding the change of the angle as well. Now I do want to come back and redo part B. And instead of using the cosine ratio, I'm going to use the sine ratio. Wait, I used the sine ratio. Let's use the cosine ratio to see what we get. So what I mean is, let me scroll back up. When I look at the triangle that we drew, and we labeled everything on our triangle here, I was looking for d theta dt, and what I said was, well, let's use sine, right? Let's use sine theta. Sine theta is b over c, and we take its derivative. We take its derivative, and we get theta prime. That involves a cosine as the derivative, and then we did a quotient rule here. So what if we had done, let's say, the cosine of theta? Cosine of theta would be a over c, and what would that do for me in terms of a differentiation formula? Now, obviously, I should get the same angle measurement. Right? Now, let me go ahead then. I want to redraw the picture that we had because I'm scrolling so far away. So we had our triangle here. We had A being 500. We had B being 60. We knew A prime was 0. That doesn't change. We knew B prime was 20. We knew C was the square root of 500 squared plus 60 squared. And we knew C prime was about 1.18. We were looking for d theta dt. So again, we used sine on the prior problem. Let's do cosine this time. And we should get the same answer, right? So if I take the derivative with respect to t of both sides here, I'm going to have the derivative of cosine is negative sine times the derivative of the inside. And then I'm going to do another quotient rule. I'm going to do bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. So I'm going to plug in all of the quantities that we have here. So again, theta prime is what I'm looking for. I need sine of theta as a ratio. So sine of theta is 60 over that radical. So I'm going to have negative 60 over that radical, which is the length of the hypotenuse, times theta prime. That's what I'm looking for. And then here we have c times a prime. Now remember, a prime was 0. So I'm going to take c times 0, and that guy is gone. And then I'm going to have a, which was 500, and then c prime was about 1.18. And then all over, I have the hypotenuse squared. So in this case, again, for theta prime, I'm just going to take the reciprocal of that expression and multiply it over. So I'm going to have theta prime. So look, check it out. Negative times a negative is going to be positive. And then I'm going to flip and multiply. Right? I'm going to multiply by the reciprocal. And I'm going to have 500 times about 1.18 was c prime. 500 squared plus 60 squared square root squared. So again, I can play the little bit of simplification game here. One of these radicals will cancel with one of those guys. And then, oops, I left my prime off over here. Theta prime. So if I plug all of this into a calculator, ooh, check this out. All right, I should be getting the same answer. And when I plug into Desmos, I don't get the same answer as we got on the last problem. So I have a mistake somewhere, and we need to go back and find the mistake. So I'm going to go all the way back to the very beginning. And from the very, very beginning, we had a value of c prime. What did we get? C prime was 1.18 feet per second. So I'm going to check that value first. So I have, what do I have? 1200 over the square root of 500 squared plus 60 squared. So I have 1200 divided by the square root of 500 squared plus 60 squared. Ooh, look, there's a mistake. So 2.38 we have roughly. So when we come back to this problem here, 2.38 should be our C prime. So let's fix that and see what we get in this situation. So 2.38. So we said we had 2.38 here. So what that changes then is this will be 2.38 here. Okay, so our 1.18 should be 2.38. Our 1.18 should be 2.38. So 2.38, this should be 2.38 here. And then I have one more time. This should be 2.38 here. Okay, so I had 60 and then 2.38. All right, so let me fix that in my calculator and let's see what we get. All right, so I changed that in my calculator and I still get 0.04. All right, so 0.039, right? If we round to 3 decimal places, 0.039, we still have 0.04, right? All right, now let's look at our second approach where we used cosine. So again, C prime should be, what did we say, 2.38 for C prime. So this guy right here should be 2.38 for C prime. So let's see how that changes my number in my calculator. So we have 2.38 here. Oh, yes. All right, they match. All right, now notice that at the third decimal place that's starting to change. But keep in mind that's because I'm using 2 decimal places of accuracy here. So if I used more decimal places of accuracy in my 2.38, if I took this deeper, then these should become more of the same. Alright, so I paused the video real quick and I actually highlighted and copied and pasted the 2.38 in here, and we can see these match much further out in decimal accuracy. So now we get the same answer as we were supposed to, regardless of the technique that we made. So both of these give us 0.039 radians per second. Right? So this was about 0.039 radians per second. Okay guys, I want to look at one more problem with you here. This problem is a little more challenging than we've done up to this point. So again, just to save a little bit of time, I typed out the problem here and screenshotted a picture. This actually comes out of Stewart's calculus textbook. So I want to talk about this problem with you and work through this. What I want to do initially is start like we've been starting, and we're going to get to a point where we get stuck, and I want to come back and figure out how we get unstuck. All right. So first of all, we're told that a water tank has the shape of an inverted circular cone with a base radius 2 meters and a height of 4 meters. If the water is being pumped into the tank at a rate of 2 cubic meters per second, find the rate at which the water level is rising when the water is 3 meters deep. So like we've been doing up to this point, we're identifying, what equation do I need to take the derivative of? And I'm being told that, water is being pumped into the tank at a rate of 2 cubic meters per second. So I have volume that's being given to me. So I know that the volume of a cone is 1/3 pi r squared h. You can always Google that if you forget. Right? So there's the volume of the cone, and then I need to differentiate. So if I differentiate like we've been doing all along, and I'm differentiating with respect to time, keep in mind here. Right? So I'm going to get lazy again, and I'm going to say we have v prime equals 1/3 pi, and I'm going to do a product rule. So I'm going to derivative of the first times the second plus first times derivative of the second. So we're being asked, find the rate at which the water level is rising. So what's the rate at which the water level is rising? So we're looking for the change of height over time, right? So h prime is what we're looking for. So in order to find h prime, I need to know r squared, I need to know h, I need to know r prime, and again, we already know r, we can find r squared, and we know v prime that's given to us. So v prime is given, and then we need to find r and r prime. Now, one of the initial difficulties here is r isn't 2. R is the change in this side here. So let me change colors. So as the tank fills, we want to know how is h changing when this is 3. So we're told we want to find out at 3 meters deep, how fast is the height changing. Now, as this height is changing, the circular top of my water is getting bigger, right? If I were to look a little further up here, right, my radius is going to be bigger. So I need to know r, and I don't know r. And in fact, I need to know r prime, and that I don't know either. I don't know the rate at which the radius is growing either. So we're stuck, and we need to get unstuck. Right? In other words, what I mean by that is we do know h. We know that h is 3. Right? And we're looking for h prime, right? That's what we're looking for here. R prime, we don't know. Right? And r, we don't know. Same thing with r. Right? So here's what we need to do. Since we do know h, what we can do is relate r to h. So if we can get r in terms of h, then we'll be able to find r prime in terms of h as well. All right, so here's how I'm going to do this, right? Let me change colors again. And I have two similar triangles here. If I look at the bigger triangle that I have here, I have this bigger triangle here. So I know in that triangle, here's 2. And I know that this is 4. Right? So here's 4 and here's 2. So I'm looking at this bigger triangle here, right? And then I'm looking at this smaller triangle here. Let me switch back to green. Right? I'm looking at this smaller triangle here. So I know that the 3 is the height. I'm looking at, man, I cannot write today. Well, actually, it's not my fault. The pen is not working. Okay, let's get the pen to work here. So we have the r, we don't know. The height is 3. So we can use similar triangles here. A couple different ways to write similar triangles. The way I like to do similar triangles is, let's say, small side to big side, small side to big side. So I'm going to say r over 2 is to 3 over h. Wait a second. All right. I don't want to say that h is 3 just yet. Right? H is changing. So in regard to that smaller triangle, what I really have is h. H is changing. I just caught that mistake. Even though I know h is 3, we will come back in a second and plug that in. But as the water fills, this is changing. So I don't know what that is initially. So if I solve this for h, let me scroll down a hair. If I solve this for h, I'm going to multiply the 2 over, and I'm going to get r is 1/2 h. All right, and then remember we need r prime here. So if I take the derivative with respect to t of both sides, I'm going to get 1/2 h prime. So if we plug in everything that we have found out now, we know v prime is given to us. Right? And we now have r. We know r is 1/2 h. We know r prime is 1/2 h prime. And then times h. And I'm running out of a little bit of room here, so let me come down. So I have r squared. Again, r was 1/2 h. So I'm going to have 1/2 h squared, and then times h prime. Okay. So let's plug in everything that we know. We were told v prime was 2. cubic meters per minute. And then we know h is 3, right? So we're finding the change in h at the moment the depth is 3. So we're going to have, let's see, we have 2 times a half is 1. H is 3. And then we have 1/2 h prime. And again, we know h was 3. And then again, h was 3. So we're going to have 3/2 squared times h prime. I'm solving for h prime here. That's what I'm looking for. Let me go ahead and multiply the 3 over, and then I'm going to divide the pi over. So I'm going to get 6 over pi. And then let's see, what I'm going to have. 3 times 3 is 9 over 2, 9/2 h prime. And then this is going to be 3 squared over 2 squared, which is 9/4 h prime. So if I get a common denominator with the h primes, what do I have? This is going to be common denominator of 4. So multiply this 2, multiply this by 2. So I have 18/4 h prime and 9/4 h prime equals my 6 over pi. So let's see, 18 plus 9 is 27. So I have 27/4 h prime equals 6 over pi. Again, I'm going to multiply the 4 over. I'm going to divide by the 27. So multiply the 4 to the 6, and I get 24, and divide the 27 over, and I get pi. And I wrote that wrong. 4 times 6 is 24. And then divided by 27 pi. So let's see, we could reduce that. 3 goes into 24 8 times, 3 goes into 27 9 times, and there's my h prime. And again, this is going to be meters per minute. Right? So I have h prime being 8 over 9 pi meters per minute. And then we could plug that into our calculator to get a decimal value for that. And we get about 0.28 meters per minute. All right, I think at this point I want to go ahead and stop. We've looked at multiple problems here where we're using implicit differentiation to take the derivative of some equation. And typically all of that equations that we looked at were geometric, right? We looked at Pythagorean Theorem. We looked at using like sine of theta equals opposite over hypotenuse. We differentiated that. We looked at a volume, differentiated that. And what I want to point out to you, what you're going to typically see in a section of this nature, if you go back and look at all of these problems, we were finding, speeds, rates of change per unit time. So when we had a squared plus b squared equals c squared, we took the derivative with respect to time of all the variables in that equation. And again, if you go back and look at all the examples, we did that with every equation that we dealt with. We're finding some rate of change per unit time. Now that doesn't have to be the case, but usually in a Calculus 1 course, when we look at applications of implicit derivatives, that's typically what we're going to see in all of the problems. All right, hope you guys had as much fun as me, and I'll see you in the next video.